Hello everyone, this is Dr. Jan. In this video, I'm going to talk about the bearing and tail-out failure for a tension member. And we're going to learn what is the bolt bearing limit state and what is the tail-out limit state and how to calculate them. And we're going to continue the tension member example and determine the bearing and tail-out limit state for the tension connections. So first, let's talk about the bearing failure. So think about we have a connection like this, and the load is applied on the plates. And if the hole is slightly larger than the fastener, and the fastener is assumed to be placed loosely in the hole, and the contact between the fastener and the connected part will exist over, as shown here, approximately half the circumference of the fastener when the load is applied. Right, so the bearing failure is like an excessive elongation of the hole in the plate. Okay. And this can be illustrated from the free body diagram. So think about we have a connection like this, and we pull out like this, and then we can see that there's the space in between the bolt and the connecting parts. And on one side and the other side, the bolt is leaning or is pushing on the connecting plates, right? So, and it is this force causing the excessive elongation of the hole. Okay. And also, the failure mode for the bolt itself is shear failure. So it tends to be sheared off along the shearing plane. Okay, the second failure mode is called tail-out failure. Okay. A possible failure mode for tail-out resulting from excessive bearing is shear tail-out at the end of the connected element. So for example, right, so it's also tend to be tail-out at the end of the plate. So that's why we call it tail out. Okay, so it's only happened at the end of the connected element. So it will only occur. So it mainly occurred for the bolt, edge bolt, but sometimes it will also, if the spacing between the bolt is too close, it will also take place between the interior bolts. Okay, so please take out your menu and find the provisions for bearing and tail-out strengths. And this part is actually in chapter J. Okay, so please turn to page 16.1-136. Okay, so let me pull out my digital menu over here. Okay, so turn to page 16.1-136. So for a standard hole, at the surface load is designed consideration. As the surface load is a designed consideration, the bearing capacity Rn is equal to 2.4 times d, which is the diameter of the bolt, times t times Fu. Okay. And then tail out at the surface load, as service load is a design consideration, so Rn, the tail out capacity, is equal to 1.2 times L times T times Fu. And LC, the definition is over here. So D is the diameter of the bolts, and LC is the clear distance in the direction of the force between the edge of the hole, and the edge of the adjacent hole. So that's the edge to edge distance, LC. Okay. All right. And T is the thickness of the connected material. Right. Okay, so let's go back to the presentation. And the phi is also equal to 0.75. Okay. So let's summarize it. So when usually we consider, service load is a design consideration for this class. Okay, so in this class we basically use this to determine the bearing capacity, and also in this equation for tail out. Why? So why there's no different factors? So why what the meaning of the factor of 2.4? Well, because the value of 2.4 corresponds to a hole elongation about 1/4 inches. Okay, so it just gives you the amount of the hole elongation. Okay, and tail out is only related to the edge to edge distance LC. So if you look at that, we can actually derive it. So tail out, assume that it's gonna fail along these two planes, so it will be equal to the shear area along the two horizontal planes times shear strength, right? So we have two planes, so times two times and the area of the shear area of the one side is LC times T, right? And typically the shear strength is 0.6 times Fu. So and we got 1.2 LC times T times Fu. Okay, so since bearing tail out is due to the elongation of the hole, so and the value of 2.4 is actually corresponds to it's an empirical value that estimates the hole elongation of about 1/4 inches. Right? Then how to determine LC, the edge to edge distance? So first of all, so for the edge holes, so for example, number 2 is the edge hole. I will call number 1 interior hole. Okay, so that's the edge hole, or we call it exterior hole. And the one closer to the load, we call it interior. Okay, so for the edge hole for the exterior hole, then LC is equal to LE, which is the center to edge distance, LE minus H over 2. Okay, so this H is the hole diameter. So that's the nominal nominal hole diameter. So it's d plus 1/16 for most standard bolts. Okay, so here we're talking about the dB less than 1 inches. Okay, and for interior, for edge hole or exterior. Okay, so for interior hole, and LC is equal to the edge to edge distance, center to center distance S minus H, right? And H is equal to D plus 1/16. So H is the nominal hole diameter. Okay, and that explains. Okay, so usually we wanna know which one will govern, which one will be controlling, right? So tail out or bearing, which one will be controlling? And if you compare, so say if tail out less than bearing means my tail out strength say tail out, right? So it's 1.2 LC T times FU, right? So if that's less than bearing, bearing is 2.4 DTFU. So FU will be cancelled out. So I get 1.2 LC less than or equal to 2.4 times D. Then further simplify to LC over RD. So means if the LC less than 2 times the diameter, less than 2 times of diameter means the tail out controls, right? Then means tail out. Tail out controls, that means my VRN for this bolt will be equal to 1.2 LC times FU. Okay. Otherwise, bearing controls. Okay, so that means if the distance is less than 2 times the diameter, 2 times the bolt diameter, then tail out will be critical. Okay, so otherwise the bearing will be controlled. So the first step is to calculate your LC and compare it with 2D. And then you will know which equation you're going to use to determine VRN. Okay, and here let's summarize it. Okay, and when the service load is a design consideration, that's what we use the most, right? So Rn is the lesser of 2.4 dt Fu 1.2 LCT Fu. When it is not a design consideration, then Rn could be increased a little bit. And when you have the long slotted holes, and Rn will be reduced. Two 2.0 DTFU or 1.0 LCTFU. Okay. Okay. Now let's continue this example. So last time we determined the yielding, the rupture limit states, and determined the block shear limit states. Okay, so now what is left is the bearing the tail out. Okay. Okay, let's look at it. Okay, so this is what we have done so far. We determined the yielding and fracture limit state for tension member and gusset plate and the block shear. So this time I'm going to determine the bearing and tail out for tension member and the gusset plate. Okay, so first of all, let's look at the tension member. Okay, tension member, so this is the tension member, right? So when P is pulled out this way, and this gonna be, this is our exterior bolt, right? We have two exterior bolts, but this is, since it is a staggered pattern, so the two exterior bolt will have the different, LC. So for this one, the center to the edge is 3 inches, and the bottom line shifted to the right of 1.5 inches. So that's 4.5 inches. Okay, so let's say this is exterior bolt 1 and exterior bolt 2, and all the others are interior bolts. Okay, let's say exterior bolt 1. And LC is 3 inches, right? Minus half of the bolt. And I got 2.53 inches. And I want to compare, so that's LC, right? So I can compare with 2D, and D is 7/8 inches. It's equal to 1.75 inches. Okay, so my LC is greater. It's greater than 2D. So that means bearing controls. Bearing controls. Okay, so exterior bolt 2 is even more farther from the edge. So I will say LC still will be greater than 2D, so also bearing controls. Right, and So then I'm gonna determine phi Rn. So phi Rn for bearing is equal to 0.75 times 2 dt Fu. So it's equal to 0.75 times 2 times d 2d. Okay, so we'll calculate it. 2d is 1.75 inches, and t, the thickness of the angle is, oh sorry, it's not 2d, it's 2.4. Okay. 2.4 dt Fu. So it's equal to 2.4 and d 7/8 and t 3/8. And the Fu 50A KSI equals 34.26 kips per bolt. Remember, that's just for one bolt. Okay. Okay. And then let's look at the interior bolt. Interior bolt. So these two are the exterior bolts, and all the others, so all the other 6 are the interior bolts. So they all interior bolts. Okay. And the LC is the edge to edge distance, right? LC. So LC gonna be the spacing. So the spacing is 3 inches, and minus the bolt diameter plus 1/16. Okay, and it's equal to 2.06 inches. And still greater than 2D. So still bearing controls. Okay, so it means all my bolts, all of the bolts are, so for all of the bolts, bearing controls, then altogether I have 8 bolts, right? So phi Rn for double angle, we have 8 bolts. All of them are bearing controls, and 2 angles. Okay, and the capacity for one bolt is 34.26 kips. Okay, and I got a number 540A. This is pretty big. This is not controlling. Okay. All right. And that's the bearing and tail out capacity for the double angle. And next, you're gonna do the same to determine the bearing and tail out capacity for gusset plate. Okay, and it's the same, but the tail outs, the exterior and interior are gonna be different. So if they pull it out this way, right? So means this two gonna be your exterior bolt. Right, so that's your exterior bolt 1 and 2. Right, because your angle is pulling this way and make these two bolts, these two holes, your edge holes, and all the others gonna be your interior bolt. So, and the distance, what's gonna be the distance? And we know that the distance from the center of the bolt 2 is just 2.5. So that's this one will be more critical. And distance from number 1 is gonna be how much? 4 inches. Okay, and you're gonna do the same, right? So you're gonna determine your exterior bolt 1 and your do the same for your exterior bolt number 2, right? So I'm sure for bolt 1 bearing will be controlling because it's pretty far from the edge. So 4 inches minus 7/8 plus 1/16, and is equal to 3.06, right? So it's greater than 2D. So it's gonna be bearing. Since it's gonna be a little different for exterior bolt 2 because it's so much closer to the edge. So 2.5 minus 7/8 equal to 1.56. Yeah, this one is less than 2D. So gonna be tail out. Okay, so let's take and all the others gonna be the same, right? Gonna be the same as your all the interior bolts. The interior bolt's gonna be bearing control. Okay, so we have one tail out. So let's calculate tail out capacity. VRN is equal to 0.75 times 1.2 LC T FU. Right, so it's equal to 0.75 times 1.2 LC 1.56, and the thickness of the plate is 0.5 inches. And in this, the gusset plate has higher strength, so the FU for gusset plate is 80. Okay, so we got 56.16 K. Okay, and then you can determine the bearing capacity for the gusset plate. Bearing, okay, so I would like you pause this video and calculate the bearing capacity for the gusset plate yourself and come back, check the result. Alright, we'll come back. And since gusset plate has the highest FU, so the bearing capacity for one bolt is higher, 63K. Okay, so all the total bearing capacity is, we have one tail out failure, 56.16 K, and plus 7 7 bearing failure, 7 bolts with bearing failure. Okay, and I got 497. Okay, and then let's complete the table. Okay, the bearing capacity we got for the tension member is 548 and gusset plate 497. Okay, so let's combine them all together. Okay, so combine them. For the tension member is 548 and the gusset plate 497. Okay, so it seems like bearing and tail out will not be controlling. Still the block shear will be controlled. So from now we check all the limit states. But remember, there is still one limit state we haven't checked yet. So the last one will be the shear. The last limit state we should check is the shear capacity of the bolt. Okay, so remember, check the shear capacity of the bolt. So that's going to be assume each bolt carry the same load. So figure out the shear capacity of each bolt and times the number of the bolts, and you get the shear capacity. And this one will be covered in the chapter of connections, bolted connections. Okay, so far we complete this very comprehensive example. Okay, so I hope it's helpful to you. All right, so goodbye. See you in the next video.